Welcome! In this session, we'll be exploring problem number 1181, titled Before and After Puzzle. This is an interesting challenge where phrases need to be combined based on matching words. Together, we'll break down the problem, analyze the approaches, and learn how to solve it step by step. Let's dive in. In this problem, we are given a list of phrases, where each phrase is a string consisting of space-separated words. The task is to create new phrases by taking two phrases and appending the second phrase to the first. However, this can only be done if the last word of the first phrase matches the first word of the second phrase. When this condition is met, the result is a new phrase formed by combining the two, without duplicating the matching word. The goal is to return a list of all unique phrases that can be generated this way, sorted lexicographically. This means the output should be in alphabetical order, ensuring no duplicates. The input is a list of strings, and the output is also a list of strings that satisfy these conditions. Let's look at an example. If the input list of phrases is writing code, code rocks, we start by analyzing possible combinations. The phrase writing code ends with the word code, and the phrase code rocks begins with the word code. Since these two words match, we can combine the phrases. The result is writing code rocks, formed by appending code rocks to writing code while avoiding duplication of the word code. There are no other valid combinations in this case, so the output is simply a list containing writing code rocks. Now consider a more complex example with multiple phrases: mission statement, a quick bite to eat, a chip off the old block, chocolate bar, mission impossible, a man on a mission, block mission. Here, there are several valid combinations. For instance, a chip off the old block ends with block, and block mission starts with block, so combining them forms a chip off the old block mission. Similarly, block mission ends with mission, and mission impossible starts with mission, resulting in block mission impossible. These and other valid combinations are included in the output. The final list of phrases is sorted lexicographically, ensuring alphabetical order. In a simpler example, if the input is a, there is only one unique phrase, which is a. While it can technically combine with itself due to the matching first and last word, this does not produce any new results. Therefore, the output is just a, as there are no other valid combinations to include. This example highlights the importance of ensuring uniqueness in the final output and handling cases where phrases may combine with themselves. Finally, there are a few additional considerations to keep in mind. First, the output list must contain only unique results, even if multiple identical combinations can be generated from different input phrases. Second, the output should be sorted lexicographically, which means uppercase letters should be handled carefully due to their distinct ordering in ASCII. Third, a phrase can combine with itself, provided the last word matches the first word. Lastly, with up to 100 phrases in each phrase having up to 20 words, it's important to optimize the solution to handle larger inputs efficiently within the constraints. These details ensure correctness and scalability in solving the problem. To begin with, one straightforward way to tackle the problem is the brute force approach. The intuition here is simple: we iterate over all possible pairs of phrases, comparing the last word of the first phrase to the first word of the second. If we find a match, we combine the two phrases by appending the second phrase, excluding its first word, to the first. This process is repeated for every valid pair of phrases, and we ensure uniqueness of the resulting combinations by storing them in a set. Finally, we convert the set to a sorted list before returning the results. While this approach is conceptually simple, it has significant drawbacks. The time complexity is quadratic with respect to the number of phrases, since we need to compare every pair. This becomes increasingly inefficient for large inputs, especially as redundant computations arise from repeatedly processing the same pairs in different orders. The space complexity is also proportional to the size of the unique resulting phrases, making this approach impractical for scaling to larger datasets. Now, to address the inefficiencies of the brute force method, we can adopt an optimized approach that leverages dictionaries to reduce redundant comparisons. The core idea is to group phrases by their first and last words. Specifically, we construct two mappings, one that associates each last word with the indices of phrases ending in that word, and another that links each first word to the indices of phrases starting with that word. Using these mappings, we can directly identify phrases that are potential matches, significantly reducing the number of comparisons. For each phrase, we simply check if its last word exists in the map of starting words, and if so, we combine it with all matching phrases. Again, we use a set to ensure uniqueness, and the final results are sorted before being returned. This approach is much more efficient because it eliminates unnecessary iterations over pairs of non-matching phrases. The pre-processing step of building the dictionaries is an added complexity, but it is outweighed by the overall reduction in time complexity, making the solution more scalable. Given the trade-offs between the two methods, we chose the optimized approach as the better strategy. The key insight that makes this method so effective is the realization that grouping phrases by their first and last words eliminates redundant comparisons, which are the main bottleneck in the brute force approach. While the optimized approach does require an additional pre-processing step to build the dictionaries, the overall time savings for larger inputs are substantial. This makes the trade-off worthwhile, as the method balances efficiency with correctness. The brute force approach, though simpler to implement, quickly becomes impractical for larger datasets due to its quadratic time complexity. By contrast, the optimized approach scales much better while maintaining clarity in its implementation. This alignment of problem-specific insights with computational efficiency is what makes the optimized method the ideal solution for this problem. The problem we're solving involves merging phrases based on word overlap. Specifically, if the last word of one phrase matches the first word of another, we merge them, excluding the repeated word, and continue this process until no further merges are possible. To implement this, we begin by defining our input as a list of phrases, each consisting of words separated by spaces. We then prepare our algorithm to process this list iteratively. At the core of this process is an outer loop that continues running as long as merges are still occurring. To track this, we use a Boolean variable called merged, which starts as true. Inside this loop, we reset merge to false at the start of each iteration, create an empty list new_phrases to store the updated phrases after each pass, and maintain a set called used_indices to keep track of which phrases have already been merged during the current iteration. This setup ensures that we process the list systematically and efficiently, preparing for the merging logic to follow. Now we get into the details of pairing phrases for merging. For each phrase, which we'll call P1, we first check if its index is already in used_indices, meaning it has already been merged during this pass. If not, we proceed to extract the last word of P1. Then, we iterate over all remaining phrases, referred to as P2. Again, we skip P2 if its index is in used_indices. For any valid P2, we extract its first word and check if it matches the last word of P1. If they do match, we merge the two phrases by combining P1 and all of P2 except its first word. This new merged phrase is added to the new_phrases list, and both P1 and P2 are marked as used by adding their indices to used_indices. We also set merge to true to indicate that a merge occurred, and we break out of the inner loop to move on to the next phrase. If we finish checking all potential matches for P1 without finding a merge, we simply add P1 to new_phrases as is. This ensures that every phrase is either merged or carried forward unaltered. Once no merges occurred during a pass, indicated by merged remaining false, the algorithm terminates. At this point, the phrases list, which has been updated iteratively, contains the final merged phrases, and we return it as the result. The algorithm employs a greedy approach, merging phrases as soon as opportunities arise in each pass. This ensures that all possible merges are completed before the process stops, providing an optimal solution. We also handle edge cases, such as returning an empty list if the input is empty, or returning the input unchanged if no phrases share overlapping words. Additionally, duplicate phrases are managed carefully to avoid unintended merges. The algorithm relies on a dynamic list to store the phrases after each pass and a set to track merged indices, ensuring that no phrase is processed more than once in a single iteration. These data structures allow the algorithm to execute efficiently and maintain clarity throughout the process. To analyze the algorithm's efficiency, we first consider its time complexity. The outer loop runs at most n times, where n is the number of phrases. Within each pass, the inner loop compares each pair of phrases, resulting in n² comparisons overall. Each comparison involves string operations, with the average length of the phrases denoted as m, leading to a total time complexity of n² *m. The space complexity is n plus m, where n accounts for the dynamically updated new underscore phrases list, and m accounts for intermediate string operations. For example, given the input phrases writing code, code rocks are fun, and fun times, the algorithm merges writing code with code rocks to form writing code rocks, and rocks are fun with fun times to form rocks are fun times during the first pass. In the second pass, no further merges are possible, so the final result is the two merged phrases, writing code rocks and rocks are fun times. The final output of the algorithm is a list containing the merged phrases, writing code rocks are fun times. This result demonstrates how the algorithm successfully combines phrases based on overlapping words, iterating until no further merges can be made. It ensures that all merge opportunities are explored while maintaining efficiency and clarity in its approach. Here, we start by importing the defaultIct class from the collections module, which will help us manage mappings efficiently. We're defining a class called solution and implementing a method named before and after puzzles that takes a list of phrases as input. The first step inside the method is to create two dictionaries using defaultIct. One maps the first word of each phrase to its indices, and the other maps the last word of each phrase to its indices. These mappings will allow us to quickly look up phrases based on their starting or ending words. Next, we iterate over each phrase in the input list, splitting each phrase into individual words. The first word is stored in the first word map, and the last word is stored in the last word map, with their respective indices. After creating these mappings, we initialize an empty set called result_set to store unique merged phrases. Now, we loop through each phrase again to find valid matches. For each phrase, we retrieve its last word and check if it exists in the first word map. If it does, it means there are phrases that start with this last word. We then iterate through the indices of these matching phrases. To avoid merging a phrase with itself, we ensure the indices are different. When we find a valid match, we construct the merged phrase by combining the current phrase with the matching phrase, excluding the duplicate word in the middle. This merged phrase is then added to the result_set, ensuring all entries remain unique. Finally, after processing all the phrases, we need to return the results in sorted order as specified in the problem requirements. The sorted function is applied to the result_set, converting it into a sorted list, which is then returned as the output. This ensures that the output is both unique and follows lexicographical order, making it easy to verify and consistent with the expectations of the problem. With this, our implementation is complete and effectively handles the task of generating all valid before and after puzzles from the given list of phrases. Here, we begin implementing the solution by defining the before and after puzzles method. The goal is to merge phrases based on matching the last word of one phrase with the first word of another. First, we create two maps, first word map and last word map. These will store the indices of phrases keyed by their first and last words, respectively. By organizing the phrases this way, we can efficiently find matches later. We then iterate through the phrases array, splitting each phrase into its component words. The first word of the phrase is added to the first word map, and the last word is added to the last word map. This pre-processing step ensures that we can quickly look up phrases with a given first or last word. After that, we initialize a result set to store unique merged phrases. Next, we begin iterating over all phrases to find valid matches where one phrase's last word matches another phrase's first word. As part of this process, we check if the first word map contains the current phrase's last word. If it does, we retrieve the indices of the matching phrases and proceed to compare them, ensuring we avoid self-merges by checking that the indices are not the same. When we find a valid match, we split the second phrase into its component words and create a merged phrase using the combine phrases helper method. This method ensures that the phrases are combined correctly, avoiding duplication of the overlapping word. It uses system.arrayCopy to copy the words from the first phrase and the non-overlapping portion of the second phrase into a new array. The merged phrase is then constructed by joining the words into a single string and added to the result set. Because the result set is a hash set, it automatically ensures that all merged phrases are unique. Once all possible matches have been processed, the unique merged phrases are converted into a list, sorted in lexicographical order, and returned as the final result. This ensures the output is both correct and meets the requirements for ordering. By organizing the logic in this way, The implementation is both efficient and easy to follow, leveraging maps for fast lookups and helper methods for clarity in combining phrases. To solve the problem, we start by initializing two mappings, first underscore word underscore map and last underscore word underscore map, both as empty default ticks. These mappings help us track which phrases start or end with a specific word. First, we iterate through the given list of phrases. For the phrase at index 0, writing code, the first word is writing and the last word is code. We update first underscore word underscore map to map writing to the index 0 and last underscore word underscore map to map code to the same index. Next, for the phrase at index 1, code rocks, the first word is code and the last word is rocks. We add these to the mappings as well. At this point, first underscore word underscore map contains writing mapping to index 0 and code mapping to index 1, while last underscore word underscore map contains code mapping to index 0 and rocks mapping to index 1. Now that the mappings are ready, we can begin checking for valid merges. Starting with phrase 0, writing code, we see that its last word is code. Using first underscore word underscore map, we check if there are phrases that start with code. Phrase 1, code rocks, matches this condition. Since the last word of phrase 0, writing code, matches the first word of phrase 1, code rocks, we merge them into a new phrase, writing code rocks. This merged phrase is added to a set called result underscore set to ensure uniqueness. Moving on to phrase 1, code rocks, we find that its last word is rocks. However, there are no phrases in first underscore word underscore map that start with rocks, so no further merges are possible for this phrase. At the end of this process, our result underscore set contains the phrase writing code rocks. Finally, we return the sorted version of the result underscore set, which is the list containing just this phrase, writing code rocks. Now let's analyze another example to understand the solution better. Here, the input phrases are AB, BC, CA. As before, we start by populating first underscore word underscore map and last underscore word underscore map. For the first phrase, AB, the first word is an and the last word is B, so we update the maps accordingly. For the second phrase, BC, we add B as a key in first underscore word underscore map and C to last underscore word underscore map. Finally, for CA, we update the mappings with C in first underscore word underscore map and in last underscore word underscore map. Now, both mappings are fully populated. With the mappings ready, we begin checking for valid merges. Starting with the first phrase, AB, we find that its last word, B, matches the first word of the second phrase, BC. We merge these phrases to form ABC. Next, for the second phrase, BC, its last word is C, which matches the first word of the third phrase, CA. Merging these results in the new phrase BCA. Finally, for the third phrase, CA, the last word is A, which matches the first word of the first phrase, AB. This allows us to merge them into CAB. After processing all phrases, our result underscore set contains the unique merged phrases ABC, BCA, and CAB. We return the sorted version of this set, which is the list, ABC, BCA, CAB. Now let's consider one more example to see how the solution handles different scenarios. This time, the input consists of the phrases 1, 2, 2, 3, 3. As always, the first step is to build the mappings. For the first phrase, 1, 2, we add 1 to first underscore word underscore map and 2 to last underscore word underscore map. For 2, 3, we update the maps with 2 in first underscore word underscore map and 3 in last underscore word underscore map. Lastly, for the phrase 3, we add 3 to both mappings. After populating the mappings, we examine each phrase for possible merges. Starting with 1, 2, its last word is 2, which matches the first word of the second phrase, 2, 3. Merging these gives us the new phrase 1, 2, 3. For the next phrase, 2, 3, the last word is 3. This matches the first word of the third phrase, 3, but since the third phrase consists of just the word 3, merging them does not change the phrase. Finally, for the third phrase, 3, there are no further matches to process. At the end of this iteration, the result underscore set contains the unique phrases 1, 2, 3 and 2, 3. Sorting the set gives us the result, 1, 2, 3, 2, 3. This concludes our walkthrough of the solution. By systematically building the mappings and using them to identify valid merges, we efficiently solve the problem while ensuring all merged phrases are unique. To analyze the time complexity of our algorithm, we can break it down into 3 primary steps. The first step involves building the first _word_ map and last _word_ map. Here, we iterate through the phrases list, which contains n phrases. For each phrase, we split it into words. If we take k as the average number of words per phrase, splitting a phrase into words takes k. Adding entries to the dictionary is an O(1) operation. Since we perform this for every phrase in the list, the total time complexity for this step amounts to n*k. The next step is iterating through the phrases to identify valid matches. For each of the n phrases, we check if its last word exists in the first _word_ map. This lookup is efficient, with a time complexity of O(1) due to the hash map. If the last word matches, we process the indices stored in first _word_ map, last word. Let's assume m represents the maximum number of phrases sharing the same first word. For each valid index, we split the second phrase into words, which takes k, merge the 2 phrases, which also takes k, and then add the resulting merged phrase to the result _set in O(1). In the worst-case scenario, where each phrase pairs with every other phrase, this step involves n*m*k operations. Finally, we sort the result _set. Since the size of the result _set can go up to n², in the worst case, sorting takes r*log r, where is the size of the result _set. Substituting r as n², the sorting step contributes n² log n to the overall complexity. To summarize the overall time complexity, in the best case, it is n*k plus n*m*k plus r*log r. However, in the worst case, it simplifies to n times k plus n² times k plus n² log n, which is dominated by n² times k plus n² log n. Shifting focus to space complexity, the first _word_ map and last _word_ map require space proportional to the number of phrases. In the worst case, where every phrase has unique first and last words, the maps have n entries, and each entry may store up to n indices. This results in n² space usage for the maps. The result _set requires additional space for storing merged phrases. Since there can be n² merged phrases, each of average length k, the result _set consumes n² k space. Together, these dominate the overall space usage. Additionally, auxiliary space is required for splitting phrases into words, which takes k space per phrase, and sorting the result _set, which uses r auxiliary space, where is the size of the result _set. This auxiliary space is bounded by n² in the worst case. Combining all these factors, the overall space complexity becomes n² k, driven primarily by the storage requirements of the result _set. When compared to a naive approach that examines all possible pairs of phrases, the optimized solution demonstrates significant improvements. The naive approach, which directly compares each phrase with every other, results in a time complexity of n² k, and a similar space complexity of n² k. The use of hash maps in the optimized approach eliminates redundant checks and enables O(1) lookups, reducing inefficiencies. While the sorting step introduces an n² log n term to the time complexity, it ensures that the output is sorted as required. The overall time complexity, therefore, is n² times k plus n² log n. As for space complexity, it remains n² k, predominantly due to the result _set and the storage requirements of the maps. To confirm the big O calculations, we note that constructing the map scales with n*k, the nested phrase matching is bounded by n² k in the worst case, and sorting is n² log n. Together, these components make the time complexity asymptotically accurate for large input sizes, while the space complexity is dominated by the result _set, confirming n² k. When solving this problem, there are several common mistakes to watch out for. First, not accounting for edge cases can lead to runtime errors. For instance, if 2 phrases have no overlap, or if the input includes empty strings, your program might behave unexpectedly. Always validate the input and test edge cases thoroughly. Second, using inefficient pairwise comparisons like nested loops for all pairs of phrases can quickly become a performance bottleneck, especially for large datasets. Instead, you should optimize lookups with data structures like hash maps. Third, case sensitivity is another area where errors can arise. If you don't normalize the input, comparisons like word versus word may fail. Decide early whether you want case-sensitive or case-insensitive comparisons, and pre-process your strings accordingly. Additionally, don't forget to trim leading or trailing spaces from phrases, as mismatches caused by whitespace can be subtle but problematic. Lastly, ensure you handle duplicate phrases correctly. Failing to do so may result in redundant matches or unintended infinite loops when chaining phrases together. In interviews, there are key insights that can help you excel with this type of problem. Recognizing patterns is crucial. Many problems involving strings or sequences rely on common techniques like prefix-suffix relationships or hash-based lookups. Being able to identify these patterns quickly will help you develop an optimal approach. Optimization is another important aspect. For instance, you can use a hash map to store the last word of each phrase as a key in the phrase index as its value. This allows for constant time lookups, significantly reducing the time complexity to O(n). Communication is also critical during interviews. Be sure to clarify your assumptions, such as whether string comparisons are case-sensitive, how you'll handle duplicates, and what the expected output should be for edge cases. Finally, consider trade-offs. While a brute force approach may work for smaller inputs, it's essential to demonstrate that you understand the importance of optimizing for larger datasets, especially in competitive or real-world scenarios. This problem also shares similarities with several related problems on LeetCode, which can reinforce your understanding of these concepts. For example, LeetCode 49, Group Anagrams, involves grouping strings based on shared properties, much like the way phrases are grouped in this problem. LeetCode 139, Word Break, focuses on breaking a string into valid substrings, which often relies on prefix-suffix relationships. Another related problem is LeetCode 1202, Smallest String with Swaps, where you need to group and reconstruct strings based on connectivity. Lastly, while LeetCode 56, Merge Intervals, isn't string-based, it involves combining overlapping intervals, which parallels the idea of merging phrases with shared boundaries. Exploring these problems can deepen your understanding of how to apply similar techniques in different contexts. There are also alternative approaches to solving this problem, each with its own trade-offs. The hash map-based approach is one of the most efficient. By storing the last word of each phrase as the key and its index as the value, you can quickly check if the first word of a phrase exists in the hash map. While this method significantly reduces time complexity to O(n), it comes at the cost of additional space for the hash map. Another option is a sorting-based approach. By sorting phrases based on their first and last words, you can use a two-pointer technique to find matching pairs. This has a time complexity of O(n) log n, but the sorting step introduces extra overhead, and the approach may not feel as intuitive as the hash map method. Finally, a tree-based approach is especially useful if the problem involves chaining phrases into longer sequences. Trees allow efficient prefix or suffix matching, but they can be complex to implement and may require significant space for large inputs. Each method has its strengths, so choose the one that best fits your constraints and problem requirements. Great job! To wrap up, we reviewed the before and after puzzle, summarized the key concepts, and highlighted important takeaways such as string manipulation and efficiency in algorithm design. Thanks for watching, and don't forget to like, subscribe, and keep practicing. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!